Hello friends, welcome to Electronic Circuit Hub. So today we are going to understand about the design and simulation of square wave inverter. How you gonna design and how you gonna simulate the square wave inverter in LTspice, okay? And then later I'm going to run the simulation and I'll show you the FFT and the fast Fourier transform, okay? I'm going to show you. Hello friends, welcome to Electronic Circuit Hub. So today we are going to understand about the design and simulation of square wave inverter in LTspice. How you gonna design the square wave inverter for your application and how you gonna simulate the square wave inverter in case of LTspice. Okay, so we are going to understand design and simulation first, and then later I'm going to show you the fast Fourier transform, and we are going to see the different harmonics components which are present in this square wave inverter. Okay, and so I'll run the fast Fourier transform. We'll see the even and odd harmonics there, and also I'm going to calculate and I am going to show you the total harmonics distortion, that is THD percentage. How this LTspice calculate the total harmonic distortion and how this tools gives you 1 percentage. Okay, for this square wave, let's say 48% is the total harmonic distortion, so that is generated by the LTspice. So I'm going to show you. Okay, so let us first understand the design and simulation, how you can build the circuit and what I have done, how you can build your own square wave inverter circuit, right? So if you look at here, so what I'm doing here is I'm using the 4 switch. You can use either IGBT or you can use the MOSFET as well, but at the moment I'm using the generic switch, that is a switch SW. So S1 and S2 here, and if you look at that right side, S3 and S4, and we have here the 4 generic switch, and I want to operate this switch in the saturation region. Okay, if I say the saturation region, what do you mean by saturation region? Means it is going to completely off and it is going to completely on. So that is mean by the saturation of your switch. So we have the 4 switch, and if you look at now the anti-parallel diodes, so in all the four switch, what I'm doing here is I'm using the anti-parallel diode. Okay, so these are the anti-parallel diode which I'm using to operate, which I'm using in parallel with your 4 switch. Okay, so that is D1, D2, D3 and D4, which is D1 for switch 1, D2 is connected in parallel with switch 2, and so on. D3 is switch 3 and D4 is connected in parallel with switch 4. Now between your switches, this is one junction, right? This is one junction, let's say, and this is other junction, and between these two junction we want to connect our load. Load could be anything. Load could be, it could be your motor, it could be any your inductive load, whatever, whatever you want to use it. Right now I'm using L1 as a load, which says that this is my inductive load. Okay, so this is all about the MOSFET, the diode, and the load connection. What about the input? If you look at here, this is V1, and V1 is the input voltage. And right now, what I'm giving here is I'm giving the 325 volt DC. So I have 325 volt DC, and I want to simulate how this square wave inverter looks like if I apply the 325 volt DC here. Okay, so now if you want to operate these circuits, how you gonna do that? If you look at here, so let us first look at here. What is the driving mechanism of your all 4 switches and how I am driving the 4 switches? It is very important to understand. Otherwise, your circuit is not going to understand, not going to work it. Okay, so circuit is not going to work. So in order to understand, if you look at here, I have used the PWM signal, that is PWM. And if you look at the S2, the driving signal for PWM, S1 is the PWM, and the driving signal for S2 is the CPWM. What do you understand by PWM and the CPWM? So PWM stands for pulse width modulation. There will be some frequency. And the CPWM stands for the complementary pulse. So in the S1, I'm giving, let's say, X pulse. So in S2, I'm giving just complementary of your S1 pulse. So I have uh, the PWM pulse and the CPWM pulse uh, for S1 and S2 and so on. If you look at here, again S3 and S2 are being driven by CPWM, and S1 and S4 are being driven by the PWM signal, right? So how you gonna generate the PWM signal? It is again very important to you to understand. And if you look at now, to generate the PWM signal, I have used two voltage source. One is the V2, other one is the V3, and you have to model your V2 and V3. Okay, so what is the V2? So for V2, if I right click on here, I'm using the pulse, and now the initial voltage is 1 volt. The on voltage is 0, delay time is 0, rise time is 1 nanosecond, fall time is 1 nanosecond, and that this T on is duty divided by switching frequency. So what is the duty? Consider this case my duty cycle is 0.5. Okay, and what is the switching frequency? Since we are going to operate our AC motors, or let's say the single phase AC motors, so in this case we want our square wave to be 50 hertz. So your switching frequency is going to be 50 hertz, and the T period is one nothing but 1 divided by switching frequency. So this is the PWM. And now if I right click on the CPWM, so again initial is 0, on is 1, and the T on is D divided by FSW, and T period is 1 divided by FSW. That is done. Everything is now set. And now what I'm gonna do, I'm going to run the simulation now. Okay, so in order to run the simulation, what you need to do is you have to go on the simulate and then edit simulation command. For now, what I'm doing, I'm using, let us say I'm simulating this for 100 millisecond, and you can also check this initial operating point solution. So I clicked it here, and now I go, this man is running here, I click on it, and let's see. Okay, so let's see first here, uh, what is what is the PWM. So this is your PWM signal. Okay, this is PWM signal, and this is your complementary PWM signal. So you have the PWM signal, and you do have the complementary PWM signal with the frequency of, let me change the color for this as well, so you will understand. Okay, so now if you see, we have the PWM. When PWM is high, the red one, when blue is high, the red one is low, and so on. When red is high, your blue is low. That means both signal is out of phase, 180-degree out of phase, both signal is. But one thing you can see here, guys, I'm not using any dead time for now, but in case of the inverter, and if you're driving your MOSFET with the PWM signal, it is recommended to give some dead time between your on and off, between your transition period. Otherwise, there is a chances your MOSFETs or switches get short circuited. So, but for now, I'm not using any dead time. Okay, let's go back again on the schematic. And if you look at now, if you look at here, my schematic, what is my DC voltage? The DC I'm giving here is 325 volt. Let's say you have, this is my 325 volt DC. And now let us see the voltage across A and B. Okay, so in order to measure the voltage across A and B, you have to click on A point, this point, and drag your cursor at B point. This is one of the easiest way. So let's see what is my A and B. Now I'm going to delete this win. I am going to show you the inverter output. Now can you see, this is your square wave inverter, and if you want to measure the frequency, you can attach the cursor and you can measure the frequency 1 and 2. So I have attached the cursor, and let's say this is my on time and this is my off time. And if I find out this, where is this? So this is here, it's not showing. So let us add the cursor again, 1 and 2. So this somewhere is this, and we are not able to face this. Let me check how I can do. It is not moving, but the frequency here is, in case of this, the frequency is 50 hertz. Uh, okay, the frequency is 50 hertz. You can see now this is your perfect square wave output. Now if you superimpose the current, you load current or inductor current on it, can you see how it looks like? This is your load current, this is your inductor current, and it is around 320 ampere. So you have 325 volt, and this circuit is capable of delivering 325 amps of the current. Okay. So based on your application, you have to look, but for now it is showing 325 ampere. So this is your output of your square wave, wherein you see your output is perfectly matching and it is square wave. Now you can see your voltage and your current both for your square wave inverter, and how your voltage and current is looking like. Okay, now what I want to show you here, let us first let me run the simulation and the let me show you the FFT. What is FFT? Let me show you first the Fourier transform, that is the total harmonic distortion. And what is the total harmonic distortion for this case is, if you look at now this table, so we have the harmonic number, and I am measuring the THD up to 31st harmonic. Okay, ideally by default it is up to 9th harmonic, but what I see here is it is up to 31st harmonics. And what you can see here is your harmonic one is the odd harmonic, okay, and your harmonic 2 is the even harmonic. Okay, so and this harmonic 1 is the odd harmonic. And if you look at this, the Fourier components of your even are, the first harmonic is 4.13 into e to the power plus 2, while if you look at the second harmonic, that is even harmonic, the Fourier content is 5.7 into e to the power minus 4. Now, what is the 6 harmonics? Minus 4. What is the 8 harmonic? Minus 4. So, what you can see from this is, this in square wave you have the dominating harmonics component, which are they are the odd harmonics, because in even harmonics what we see is they are more or less close to zero. But in the case of odd harmonics, we see the amplitude, we see the Fourier component, and they are the positive value. Now let us go and look at the total harmonics. Okay, so what is the THD, total harmonic distortion, for this square wave is 48.3, and that is being generated by the tool itself. So this tool generated and calculated the total harmonic distortion for your square wave components. Okay, what is the total harmonic distortion, and what do you mean by the total harmonic distortion? It is also important to understand. Okay, so what is the total harmonic distortion in case of the square wave? Your fundamental frequency is 50 hertz, and in your fundamental frequency, what are your noise frequency which are superimposed in your fundamental frequency, that represent basically the harmonic components in your fundamental frequency. The harmonic components are harmonic content in your fundamental frequency, and it is around 48%. So now we might think, what is the square wave? What is the ideal TSD for your square wave inverter? Correct? What is the ideal frequency for your square wave inverter? And it could be 48%. Okay. If you're talking about the sine wave, it could be less than 5% or 3%, but if you're talking about the square wave and if you have the motors and inductive load, it could be up to 48%, 50%, or even less than that. Okay, now this is all about the Fourier transform and how your LTspice is generating the THD, how it is calculating the THD percentage. Okay, now let me run the fast Fourier transform, okay, for your voltage and current. Okay, so in order to run the FFT, this is your voltage, and let me see, this is your current. So you have now your voltage and current, and we have the voltage and current. Go at view and run FFT. So I am going to run FFT for both. Uh, how I can run it for IL1, and let's see if I can also run for no IL1 and then VA, VV. Ideally, it has to be VA minus VB, but let's see. Let's see. Okay. So select the waveform. Let's say VA. Let's look at first current. Okay. So this is your harmonic components for your current. Now, if you see, this is what is this? This is your fundamental frequency, and now this is your which harmonic I see here is 150. So this is your fundamental, this is your fundamental, this is your third harmonics 150 hertz, this is your 252 fifth harmonic, and this is your seventh harmonic, that is 350. And what you see from this current harmonics, these are the current. We are trying to understand the harmonic component of your inductor current or the motor current. What we can see here is we do have the harmonics present on your odd components. So we have the odd harmonics, but we don't have here the even harmonics. So for even harmonics, you will see you don't have anything. That means in case of the square wave inverter, what we see here is we only have the uh, odd harmonics. We don't have the even harmonics. Let us now look at the harmonics for your voltage, output voltage. So in order to do that, let me check VA how it looks like. Okay, and what we can do it here, basically this is VA and we can write it here VEV. Let's see what is going to show. Now unknown voltage range, I want to do with both VA and VV. Let's see now. Unknown voltage requested, how we can do, because what is my output here, what I'm trying to understand is VA minus VV, this. Okay, this is the voltage, and for this voltage I want to understand I want to look the harmonic component. Let us place this. It is not there, so let me delete. Let me try one more time it if it works. So do we have any math operation here? So I want VA and I want VV. So then click OK, and they are saying the VA and VV. Let's see. Okay, they are not okay. Both are superimposed. Now what I want to do here is I want to do VA B. No, they are not taking VA minus VB. Let's see. They are not taking. Okay. Hmm. So I don't know why, but let us look at the individual voltage harmonic component available at the node A and the harmonic components available at the node B. Okay, let us look at both. So in this case, what you see, this is my fundamental frequency. If I say the fundamental frequency, that means it is 50 hertz frequency. And where you see the notch here, we do have the dB label, that is 50 hertz. And now if you look at this notch, okay, what about this? This is the again the third harmonic. This the frequency here I can see is 150 hertz, and here the frequency is 250 hertz, and here the frequency is 350 hertz, here the frequency is 450 hertz, here the frequency is 550 hertz. So what we see from your voltage output components, we do have only odd harmonics presents on your square wave inverter. We don't have the even harmonics present. Okay, so in case of the even harmonics, you can see here everywhere we don't have anything. That is why you will see the first harmonic component, then you will see this free space here. That means in this place there should be a even harmonics, but we don't have it. And in the third place, then again you see, in the fourth place you don't see anything, and likewise and so on. Now what we saw in the um, THD calculation, we saw that we did not have any even harmonic components. They are very close to zero, and that's the same thing what we can see in the case of FFT analysis, the fast Fourier analysis. We do have only the odd harmonics component present on it. We don't have any even harmonic components present. So hope guys you understood how you gonna design the square wave inverter in the LTspice, how you can simulate it, and also how you can look at your output